So what we're going to do today is we're going to continue talking about Java parallel streams internals, focusing on how results are combined. So if you recall what we've talked about up to this point, we've talked about the splitting phase, we've talked about the applying phase, and now we're going to talk about the combining phase. And we'll show how streams are set up to be able to combine partial results into a single so-called reduced result. And as always, you can find out more about all this stuff by taking a look at the article by Brian Getz, which is in the link at the bottom of the slides. So if you recall, last session we talked about how the common fork join pool finished processing chunks of partial results, and those were all run in parallel using threads from the common fork join pool. And now we're getting ready to merge all the results together, combine all the results together by joining them into a final result. And we're going to assume, for the sake of this discussion, we're talking about a so-called non-concurrent collector. Very shortly we'll explain what that means in more detail, and we'll especially talk about how there's also other forms of collectors called concurrent collectors. The way that this occurs from an implementation point of view using the fork join framework is that the joins occur in a single thread at each level in the hierarchy. So as you come out of the processing of all the different subtasks or sub-data sources in parallel, where each thing is done sequentially, of course, then there's a parent that's going to wait for its children to finish, and those children are joined together in one thread. They're joined together in one of the threads, and that happens recursively until you have only two children or sub-children or whatever you want to call them that are ready to be joined together by their parent. And the final parent at the top puts everything back together again, and that constitutes the complete result. Because everything is done by joining in a parent in a single thread, even though there's lots of threads, each pair of things come back are joined in a single thread. There could be multiple of these joins happening in parallel, of course. There's no need for any synchronizers during the joining. So the joining phase is done without synchronization, well, without you, the programmer, having to synchronize. Of course, there's synchronization occurring under the hood to be able to make sure that the data caches are flushed properly, et cetera, et cetera. Different terminal operations combine partial results in slightly different ways. For sequential streams, not that big of a deal. For parallel streams, it's a big deal. So of course, we're going to make a big deal out of it because we're talking about parallel streams at this point. So the thing to remember is that reduce will create a new immutable value by joining together other immutable values. And the assumption is it's immutable, and we'll talk about what immutable means. Basically, immutable means once the values are set, they can't be changed. That's what it means to be immutable. So here's a very simple example that we've talked about before. We'll just kind of reiterate it and kind of visualize pieces of this. So you can see here we're going to start out with a range of longs from 1 to 8, and then that gets subdivided up smaller and smaller until we get to the point where we're multiplying two things together. And that, of course, will happen sequentially in parallel, right? So we'll have a number of different tasks that could all run in parallel, but they'll be doing sequential things, like they're multiplying 1 times 2 to yield 2, 3 times 4 to yield 12, 5 times 6 to yield 30, 7 times 8 to yield 56, etc. And then you can also find this example in my GitHub repository in EX16. And this is kind of what it looks like. So the reduction takes place by multiplying the values together in a pairwise fashion. This uses a lambda expression. You can also use a method reference here too. And this reduction takes place recursively, or backing out of the recursion probably is a better way to look at it, as we go up the tree or down the tree, depending on whether the tree grows up or down in your mind. So you can see that we then take one thread, we'll take 2 and 12 and multiply it together to create 24. Another thread will take 30 and 56, multiply it together and produce 1,680. And then 24 times 1,680 yields the final result, 40,320. I always have to write that down because I don't remember multiplication at that level. I can do the first row up here and part of the second row. So the idea here is that we're taking, at every step along the way, we're taking two immutable values, longs, and multiplying them together to yield a new immutable value. And it's very important to understand that those values are meant to be immutable. And you'll see why when we get into some of the subtleties of this shortly, because if they're not immutable, then chaos and insanity will ensue. In contrast, collect mutates an existing value. And here's an example that we've talked about before, and I'll point you to some other places to learn more about this. But basically, this particular example is going to take the complete works of Shakespeare are actually the complete words of Shakespeare. So this particular little get input method takes the complete works of Shakespeare and then breaks them up by word. So we end up with all the words in Shakespeare. And then the way that this works when we use parallel stream is the splitterator process will take over, as we've talked about already. And so we'll end up first with splitting all the words in Shakespeare into half the words of Shakespeare, the first half, followed by the second half. That'll be split. And then that'll be split into, a quarter of the words, the second quarter of the words, the third quarter of the words, and so on. And that'll split until we end up with all the words of Shakespeare sort of one at a time. And then the merging process, the combining process will take place. And the way this is going to work is we're going to use something called a tree set. And as you probably recall from earlier discussions, a tree set is something that's going to be, it's going to guarantee unique values. So a tree set will have only one of every word. So what we're basically trying to do is, as you can see here, get the unique words of Shakespeare. And as this is taking place, as we back out of the recursion, as it were, then we're going to end up collecting things together into many different tree sets for the subset results of all the words that are being accumulated. So, we'll start out with a tree set with just a couple of elements in it, and then that will be merged, and then we'll have more, and that'll be merged, and that'll be merged, and that'll be merged, until we finally end up merging together the last two tree sets into the final tree set. So the final tree set would, of course, contain all the unique words. And the idea here, it's important to understand, is that collect, by design, is intentionally mutating a container, a tree set in this case, in order to accumulate all the results that it's producing. Now, we'll talk later, when we talk about concurrent hash sets, there's another way when we talk about concurrent collectors, we will use something called a concurrent hash set collector in order to avoid all that merging. So the problem with this approach here is that we have to merge. We're merging all these sets together, and merging sets takes time. Merging lists takes no time at all, right? You just tack one at the end of the other. So it's basically a constant time operation. It's an array list in particular. But merging tree sets takes more time. So an alternative approach, which we'll actually benchmark and quantify, is to use what's called a concurrent collector, where all the different threads will all store the values into one concurrent collection, which is this thing called a concurrent hash set, which is basically my little wrapping of concurrent hash map to make it a set instead of a map. And we'll take a look at that as well. It's pretty cool. So this is just a quick overview of the internals of parallel streams as it relates to combining results. So the key thing to remember from this discussion is that whether you use concurrent collectors or whether you use non-concurrent collectors, things are collected together mutably, so you end up with a single result which contains whatever is the right data structure for the designated collector factory. So in this case, we used a hash set. In the other concurrent hash set, in the other case, we used a non-concurrent tree set. And so collect mutates existing values, reduce expects to create a new immutable value. And keep those things in mind as we go on to the next discussion, because it's going to make a big difference.